Hello everybody, today we will show you a nano-power consuming Buck-Boost DC-DC converter for battery operated and energy harvesting applications. With the introduction of the RP605 Buck-Boost DC-DC converter, we have made a large step forward in designing power management ICs with an ultra-low current consumption. It has an emphasis for use in battery-powered devices like wearables, IoT applications, wireless sensor modules, as well as in circuits for energy harvesting. To reduce valuable circuit board space, the product only needs 3 external components and one has an option to choose from 2 packages. In particular, the RP605 is suitable to use when a supply voltage is required somewhere in between the voltage level of a fully charged and a fully discharged battery. At a certain point, the DC-DC converter automatically switches from buck to boost mode and vice versa. In this example, the Buck-Boost has a significant advantage above the regular buck DC-DC converter, as it maintains the output voltage setting even if the input voltage drops below the output voltage setting, resulting in a longer operation lifetime of the application. The RP605 is especially designed for applications that are primarily in sleep mode and are periodically activated to take a measurement, send data, and then return to sleep mode again. For this type of application, the current consumption in sleep mode must remain as low as possible. The RP605 has an impressive low quiescent current and uses only 300 nanoampere, which extends the battery life or allows the designer to select a smaller battery for the application. The operating voltage of the RP605 ranges from 1.8 to 5.5 volt and delivers up to 300 mA in buck mode, while in boost mode the output current is less and related to the input voltage level. As for the output voltage, it is internally set by laser trimming from 1.6 to 5.2 volt in a 0.1 volt step rate. Peak efficiency is around 92% depending on input and output conditions. The RP605 has an optional automatic discharge function, which quickly discharges the output capacitor as soon the chip is disabled by the chip enable pin. The additional battery monitor circuit is one of the key features of the RP605. A conventional way to measure the remaining battery charge is using an external resistor divider plus MOSFET connected to an analog to digital converter. However, the input impedance of the analog to digital converter is typically low and the resistor divider impedance should be low as well, resulting in a considerable current flow to ground. It is draining the battery and limiting the lifetime of the application. The RP605 provides a simple solution with a built-in resistor divider and voltage follower as a buffer. This circuit has a much lower current flow to ground and the BM output is compatible with the input impedance of the analog to digital converter. Additionally, all essential components for this circuit are integrated into the chip, reducing valuable circuit board space and cost. This slide shows an example of how to use the battery monitor. One can compose a simple 3-stage fuel gauge to measure the remaining charge left in a coin-type battery. The battery voltage is used to indicate the 3 stages of the battery and advises to replace or charge the battery as soon the voltage reaches its lowest level. The RP605 has a number of safety functions that protect the IC and other parts of the applications against possible damage and defects, such as undervoltage lockout. The DC-DC converter is switched off in case the input voltage falls below a minimum threshold. Soft start regulates the output voltage to smoothly rise and prevents any output overshoot and undershoot during the startup period. Alex current limit prevents peak current through the inductor from exceeding a specific maximum current threshold. Output overvoltage protection turns off both the P-channel and N-channel MOSFETs. Thermal protection switches the IC off in case the junction temperature rises above 140 degrees Celsius. Target applications for this product are small devices powered from coin batteries, a USB port, or even from an ambient power supply, such as low power wireless communication equipment, low power CPU or MCU, memory and sensor devices. It is also very suitable for use in energy harvesting applications to optimize the voltage supplied from a capacitor or cell for energy storage.